So hello everybody, welcome back to our whole training series. Today we have another tutorial on transformers. I'm very happy to introduce Priyam Mazumdar, whom you already probably know quite well because he already presented some tutorials on other topics in this series. And of course, transformers is one of those technologies that are kind of becoming very, very widely used and in all kinds of domains. And so Priyam is going to give us an introduction to how to get started with transformers. So Priyam, please take it from here.
So we're going to go ahead and code up the vision transformer. I'm just re-recording this because we had the Wi-Fi issues when I did it live. So we're just going to go through it again. And hopefully if you can watch me code it up, it'll make a little bit more sense. So this time I can, I converted it to a Jupyter notebook so I can kind of point things out as we go, just so I can make sure we understand how we're going from these images I drew to the actual code itself. So we'll get there in a bit. I do want to mention that these are kind of the 4 places I referenced when writing this up, and it's basically a simpler version of some of this, and I use the Karpathy's MinGPT for his attention implementation. Things a little bit clearer compared to the one I had done initially. So let's just go ahead and start putting this together. So technically, as I promised, all we need is torch and import torch.nn as nn, right? So we're gonna code everything with torch on its own, but later on for the actual training purpose, we're gonna be doing a dogs versus cats just to make sure that the model is functional. We just need to go ahead and just import in all the other things we need. So we're gonna do a numpy as np, pandas as pd, import torch. Actually, it'll be from torch. We want to import in optim, right, or optimizers. And now we need a data set and a data loader, so that sits in from torch.utils.data, import data set, and the data loader. More specifically, we want a image folder, so we're going to do from torch vision data sets. We want to import image folder so we can quickly stream these data sets together. Then we would need from torch vision transforms. We want to import in our typical things. We want to compose together different transformations to be able to normalize, and we'll just use the ImageNet weights later. Random horizontal flip, right? A resize so we can make sure everything's the same shape, and to tensor, right? There we go. So that's everything we need. And then just as a progress bar from tqdm, we want to import it tqdm. All this should look pretty familiar. I used almost all of this in the PyTorch tutorial, so that's all in there. But as a quick recap, right? So we're basically I'm going to quickly recap all the images, and then we're going to code it up. And you can read through this if you reference this notebook on your own later. I'm just going to kind of explain things as we go. So we're going to be doing images of size 224 by 224 with patches of 16 by 16, and we need to take each of these patches and embed them with 768. Now, technically, we could write our own patching function to take an image, split it up into patches. We'd get a 16 by 16, flatten it, and then, use a linear layer to turn the 256 to a 768. I don't want to write that patching function, so we can actually directly use the convolution mechanic. I know we said there is no convolutions in this, but we're going to use just this one to save us a little bit of effort, and it seems to work pretty well for all the testing that I've done. So this is our patch embed, right? So these will be our patch embeddings. It'll be nn.module, right? And like always, we need to initialize it with self. We will need to set the image size. We're going to set to a default of 224. The patch size will be a default of 16. You can expect 3 channels because it's a RGB image, and then we're going to do an embed dim of 768, right? And so let's do a quick pass here, and then we also need to define our forward function, again self and x, and put a pass in there. So let's just call this here patch embed. And just so we can see the tensors as we go, just so we can see the shapes as we go, we're going to do a quick rand is equal to torch.rand n. And we know an image, right? If we have two images, each image will have 3 channels and then be 224 by 224, right? So we have our some just random tensor that we're going to pass through. This is just for validation. So, all right, so let's go ahead and do this. So let's do self dot image size is equal to the image size. Self dot patch size equals patch size. We're going to save all these as variables for the class. Self dot enchans equals enchans, and then self dot embed dim equal embed dim. Right. So these are all our environmental variables or class variables. Next, we need to calculate, how many patches can we expect. So if we have 224, right? If our image is of size 224, we're going to find out the number of patches. It'll be 224 divided by 16, and then essentially it'd be that many patches squared, right? Because we have a square number of patches. So right, 224 by 16, that should give us 196. But we're going to do self.n patches, right? How many patches we can expect. Patches is going to be equal to our image size, integer division by the patch size, and we just need to go ahead and square it, right? Just so it's all good to go. So that's the number of patches we can expect. So now we're going to create the projection, right? So how are we going to take this image and project it to this thing? Like I said, we're going to use this convolution mechanic just to, again, save us some work. So our typical conv2D, the in channels, right, will be the enchants that we had. Our out channels equals the embed dim, right? So we're going to go from 3 channels in to 768 channels out, right? That's the embed dim we want. And how big of a filter size we want, we're going to do, or kernel size, I guess, as they call it, kernel size is going to be equal to the patch size, right? So we want a kernel of size 16 because that's the patch we're interested in. Now, typically when we do convolutions, we'd have a single kernel of size 16, and then it would move over just 1 unit, right? And so, or like a stride of 1, right? So if you only move over a stride of 1, then the first placement of the filter and the second placement of the filter have a massive overlap. We want essentially to cut this up by doing non-overlapping filters. So we want a kernel or a filter of size 16, and we want to shift over 16. So the next one over will be its own filter or placement, essentially, of size 16 that's non-overlapping with the initial one, right? So we're going to go ahead and then set the stride, and this will also equal to the patch size, right? And when we do a forward, we're going to do x equals self dot the projection, right, of our x, and let's just print x dot shape and just see what it looks like. So we can then do pe dot forward rand and see what broke. Can't assign. I forgot one quick thing. We need to do a super here dot init, right? We didn't initialize our parent class. There we go. All right, so we can see that we have from here, we have a shape of batch size by 768 by 14 by 14, right? In the fully kind of finished Jupyter notebook, I will write out all the, what do you call it, the tensor shapes on the sides. I don't want to type all that out, so you can just take a look at that as you watch the video and just reference it. But yeah, so we can see we have a size of 2, 768, 14 by 14, which is good, right? So we have essentially a grid of 14 by 14 patches, and each patch is represented by some vector of 768. But we actually want it to be in this form, right? We want our patches, the number of patches, to be the first dimension and 768 to be the second one. So first we need to take our 14 by 14 and just multiply them together to flatten it, essentially, to get the 196 patches, and then we need to transpose it to get 768 seconds. So let's go ahead and do that. So x will be equal to x dot flatten, and flatten every dimension after the second one. So 0, 1, 2, so 2 and 3 will be flattened together, and now you'll see we have our 768 by 196, which is good. And then last we need x equals x dot transpose, right? And we want to transpose the first dimension and the second dimension. So we're going to do transpose with 1 and 2, and there you go. So there we go. So each batch or each sample in our batch has 196 patches and is embedded in some 768 length embedding. So this is essentially our patch embedding. So this was really the main thing that the Vision Transformer paper added on top of the typical Transformer paper, because in terms of how NLP works, this would say that we have 196 tokens, words, characters, whatever, and each of those are represented with a dimension of 768. Well, for us, it's not tokens, it's patches of an image, but the idea is essentially the same thing. So there we go. There's our patch embedding done. Now, this next part we're going to actually add later when we actually define the final transformer architecture, but just so we know why I will pick shapes, or what shape I'm going to pick, is our patch returned a 196 by 768, but really it's not 196, it's going to be 196 plus 1 at the end, our CLS token that we concatenate onto the end, right? These learnable parameters that we're going to hopefully kind of learn all the information or move all the information of these embedding layers and kind of move them into here. And so someone in the when I was giving this tutorial live asked, why is it that we only use this last layer for our prediction, right? Why are we depending on the aggregation of all this images, all these patches of 196 patches to somehow accumulate in this single vector? That's true. This is the way that the Vision Transformer paper did it. It's the way that BERT does it with their CLS token. There are other ways where you can actually do like an average pooling or a max pooling across this and then not even use the CLS token altogether. But I just want to stick to the original implementation that the Vision Transformer used, and I'm sure they tested different things, and this would seem to have worked best for them. So we're going to actually pass into our transformer a 197 by 768, which gives you an idea of why I'm picking those tensor shapes as I kind of demo things as we keep going. Next, we have to add in those positional embeddings. Again, this is going to be implemented in the final part, but we're going to add, essentially another set of these learnable parameters to our kind of data matrix, so to inject some learned positional information, right? So yeah, let's go ahead and quickly talk about the single-headed attention, right? And then we're going to take this and expand it to the multi-headed attention. This is the implementation that I kind of borrowed the idea from the Karpathy's MinGPT, just because I like the way he set it up. So we're just going to do it that way. So, right, so we're going to take our input data, 197 by 768, and we're going to create 3 different linear layers, a Q, a K, and a V, right? And each of them have their own weight matrix, right? As we had talked about, we're going to do a linear layer, take an input of 768, a output of 768 for now, because it's a single head, and we just need to then do this computation, right? Where we first do the attention matrix, where we do Q times K transpose. We then need to divide by the embedding dimension, and then we need to take the softmax and then multiply it by our projected value matrix, which will give us an output of the exact same shape we started with. So, and right, it's called a weighted average again, because if our attention matrix only had a 3 by 3, so imagine we have a sequence of 3 by 3, if you had 0.2, 0.3, 0.5, that's really just the weights of the value, or a weighted average of our value matrix. Could be 0.2 times the first one, 0.3 times the second embedding, 0.5 times the third embedding, so on and so forth. So let's go ahead and put this together, right? So we're going to call this class the head. So this will be class head. Again, we need nn dot and where'd it go? nn dot module, right? And we're going to, again, same as always, self. We need the embed dim equals 768. What else are we curious about? The head dim, right? So for now, because it's single header attention, we're going to take an input of 768 from our original embeddings and output 768 to maintain the same shape. So for now, we're going to set it as 768, but this will change later. And there's some dropout that we need to add in here as well. So we're going to add a dropout in there. And so we're going to do a super dot init, right? And then we're going to pass def forward self x, again pass, and now we're going to call this head declare this head module head, and then we need to create a rand tensor is going to be torch.randn. Let's stick to that same batch size of 2, but now we know we're going to have 197 tokens or patches, or 196 patches plus 1, and then a 768 embedding. Right, so quickly print out the rand again, just make sure it worked, and there we go. Right, back to normal. We have another random tensor. This would be essentially the output of our projection plus that class token added onto it. So let's go ahead and define things again. So we need the self dot query. Right, we're gonna have a query. We're gonna have self dot key, and then we're gonna have self dot value. Right, and each of these is going to be nn dot linear. It's going to take a input of the embed dim, right, because that's what it's expecting, and it's going to output head dim, which for now are the same thing, but later will change, as we saw with multi-header detention. So we're going to copy those in, right, and notice how it's 3 different ones, right? So it's 3 separate weight matrices, so they all have their own set of weights, 3 different linear layers. Then we're going to do a self dot attention dropout, and this will be a nn dot dropout with the dropout with the attention p. There we go. Cool. So that declares everything we need for this. So what we need to do is we're going to do this one at a time. So first we're going to make sure we have all the shapes correctly. So we're just going to grab them here rather than set environmental variables. So the batch size n patches, but technically it's n patches plus 1, and embed dim will be that x dot shape. Right, so basically our 2, 197, and 768. After that, we're going to do q equals self dot query x, v or k equals self dot key x, and then v equals self dot value x. So notice how the same x goes through 3 sets of their own unique projections, right? Now we're going to create the scaled attention matrix, so SAM, and this is going to be, like we saw, it'll be Q times matrix multiplication, K dot transpose, right? And what are the dimensions of the transpose? Well, Q and K have a dimension of batch by P plus 1 by 768, so we want to flip the P plus 1 and the 768, so it'll be the -2 dimension with the -1 dimension, or you could do more, but we're going to reference it from the back. So it's going to, you could have also done 2, 1 just like before, but for now let's do -2 and -1, right? So k dot transpose, there you go. So that's going to, yeah, well, let's take a look at the shape actually. So before I do the scaled part, let's print sam dot shape. Okay, good. So let's just do h, and then dot forward, it's going to be rand. So you can see we have a 197 by 197. Let's also just quickly print out the k dot shape. Right, so you can see k is of dimension 197 by 768, and then k transpose, right, dot shape will be just flipped, so it'll be 768 by 197 now. So we just flip the 2 dimensions, which lets us do our matrix multiplication. Otherwise the the shapes won't match for matrix multiplication. The only thing that's left to add here is our embed dim times -0.5. Yeah, cool. Right, because we need to divide by the square root of the embed dim, right, just like we saw, to make sure the variances match. So yeah, like we saw, this is going to have an output of a 197 by 197, essentially our our attention matrix. But to make it a proper attention matrix, we need to do SAM dot softmax, right, just to make sure it all add to 1. So let's actually show that print SAM. Right, here's our SAM values. Softmax needs a dim, so ignore that error for now. SAM dot sum, and we want to sum up axis equals 1, right? So we don't add columns, we want to add rows, and you can see this is what our scaled attention matrix currently adds up to. And then if we do dim equals -1, so along the last dimension, we want to print attention dot sum axis equals 1. And let's hide this one. And you could see there'll be values much closer to 1, right? So this is kind of what we want. Cool. So now that we have this, that gives us our attention matrix, softmax. All we need now is, again, if we print out attention.shape, the shape hasn't changed. We just added some stuff together, so it's still 197 by 197. We're now going to take this scaled softmax attention matrix and do our weighted average, essentially, is going to be that attention, ATTN, and multiply it with our V matrix. And then we want to return weighted average. I can't spell today. There. And just to quickly check, we can print out the shape of this as well. And let's see what went wrong. And so ATTN, there we go. You can see it's a 2 by 197 by 768. So weighted average is exactly the same shape as x. So we can do print x dot shape, and you can see how weighted average and x have the exact same shape, which is great, right? So transformers are, it's not an identity function, but it returns like the same shapes regardless. So there we go. So there's our single head, right? Not too complicated. Now, how do we take this and expand it to multiple heads? So like we talked about, after we do this projection, instead of projecting to 768 like we did previously, we want to project to the embedding divided by the number of heads we want. So in our case, if we want 12 heads, it'll be 768 divided by 12, giving a dimension of 64. So we're going to use linear layers of 768, and we want to head dim of 64 instead. So after we do that, we want to repeat that calculation 12 times, once per head, and each head will have its own unique weight matrix, right? So its own unique linear regression. So we're going to have 12 sets of Qs, 12 sets of Ks, 12 sets of Vs, right? So many Q, Ks, and Vs, and so it's called multi-headed attention. So we're going to do class multi-headed attention again, and then module. Whoops, don't need to mess with that. Def init, just like always. And then in this one, again, we need the embed dim, right? We need the number of heads that we want, so num heads equals 12. Let's actually put these in defaults. 768 num heads, and then we need, again, the attention p will be equal to 0, right? Just to make sure we do a maintain that dropout, and you can put whatever number in here you want. And then we need the projection, right? So after we do this concatenation, right, we put it all back together, we get the same shape, that's great. Then we need to do a linear layer, because you've just concatenated a bunch of different unique heads together. We need an opportunity for all that information to mesh together once, so we have to add a linear layer here at the end, which is fine. We just need to actually add a dropout on this linear layer too, to kind of match the implementation again. So again, super dot init, right, just like always. And now what we want to do is go ahead and just kind of define things. So self.head size, so what's the size we want? Each head should be embed dim divided by num heads. Now obviously these numbers should be divisible, otherwise this isn't going to work. So you could add in assertions and exception errors and all that, but we're going to just assume it's divisible for now. And then self.heads, right, because we're going to have 12 of them in our case, is going to be equal to nn.module list. So PyTorch has this thing called module list, which lets you basically store a bunch of individual PyTorch modules as like a list that's easy to access later on. Reason you can't use it as a list is because it won't be saved as like an attribute in the model then, so we just have to use module list here. This module list is going to be head. It's going to be embed dim. It's going to, right, because head takes in, remember the outputs for head. Head takes an embed dim, a head dim, and the attention piece. So let's just copy these actually, just to make it easy for us. So we're going to do head embed dim, but the embed dim is going to equal to embed dim, right, what we start with. The embed the head dim, right? So this one is going to equal to self.head size because we're going to go from 768 to 64 now, and the attention P is just going to equal to attention P. So whatever we set for blank in range num heads, right? Because we want to repeat it 12 times in this case, so num heads. Cool. So there's all of our heads, and then just the last couple of things, right? So another projection, which again is that meshing, will be the nn.linear embed dim to embed dim, right? And then a self.proj drop will be an nn.dropout, and this dropout will be on proj p. Perfect. Cool. So now we can do our forward self x. Again, did I save that from before, or did I already delete it? I already deleted it. That's fine. So again, we need a pass in here for now. H, or multi-headed, I guess, will be our multi-headed attention. Oh, there we go. Cool. Sorry about that. This is gonna be multi-headed attention. I'm going to leave the defaults in there for now, so that's fine. Rand will be torch.rand. Again, it'll be 2 by 19197 by 768, right? And then we're going to do mh rand, right? So just like before, what we need to, actually, let's print out self.heads first, just so you can see what it looks like. If we print out self.heads, you can see it's a modulist with each head having a query, a key, a value, and this attention dropout, right? Those are the attributes inside head, and we have 12 of them, right? So 0 through 11. And so what we need to do is iterate through our module list and kind of just pass it in. So we're going to do out is going to equal to hx for h in self.heads, right? So we're going to essentially create a list of stuff, and if we print out, it will be essentially a list of tensors. So here's tensor 1, and you can see that there's just like a whole list of tensors in here. We don't want it as a list, right? Because we want to concatenate everything together. So we're going to do torch.cat, and we want to make sure we concatenate on the last dimension. So our 64 should all kind of stack on top of each other to make our 768. So we're going to do a concatenate with dim equals -1. Dim equals -1. And if we print out, right, there's our output. If we do out.shape, right, we can see that we're back to that original shape that we started with, which is great. So this is essentially that multi-headed attention happening in, one kind of nice calculation. Now we're going to do out equals self.projection drop, self.projection proj of out. Right, so we're going to do that, and then instead of pass, we're going to return out. Cool, and you can see it outputs this thing, and this output has shape 2 by 197 by 768. So notice we just passed through 12 heads, a single transformer block with 12 heads, and our output shape is exactly the same as the input shape, right? So again, we're going to use this to our advantage. I know I keep saying this over and over again. It's really nice that this property works out, just for convenience's sake. So, all right, cool. Now we're going to go ahead and implement the sufficient attention, right? So you can see how it's not really, it is actually more efficient. So you can see how we have our head here, we have our multi-headed here. We're going to first put them together, but more important than that, see how we're doing hx for h and self heads. This is this happens in sequence. It's a for loop, but we obviously want to parallelize as many things as we can because it is a GPU. So we can actually do all this in one fell swoop with a lot of annoying matrix manipulation. Now, this might not make sense on the first go through. So in the GitHub, there is kind of line by line. Again, I wrote down exactly the shape of every tensor step by step so you can see what happens. But I'm going to first copy the top part of this so I don't have to type it again because it's all the same as before, right? So we have our embed dim, num heads, head size, QKV, attention dropout, projection drop, right? Now what's changed, first thing is, or the main thing that's changed is, instead of having a self.q, self.k, self.v, we're actually going to do it with a single linear layer, right? So we're going to take our QKV, we're going to take our input 768 and upscale it to 3 times 768 because we need 3 of them. Then we're going to essentially index and grab specifically our QKV. So let's go ahead and do that. So again, I should stop deleting that, but let's call this efficient attention, right? And embed dim is equal to, let's set these, so again, 768, num heads is equal to 12, and let these be equal to 0 and 0 for now. Cool. So we have efficient attention. All right. So we again have to create the rand again. So torch.rand 2 by 197 by 768. Right. So that's the tensor we're going to pass in. All right. So let's create our forward function. Def forward self x. Okay. So just like before, we're going to grab the batch, patches, and embed dim is equal to x.shape. Right, we're going to just make sure we have that information in here so we can use it. Now what we want to do is QKV is equal to self.QKV, and then we're going to pass in x. Right, so let's print x.shape. So I'll just print it out as we go, but it is a little bit confusing. So if you don't get it on your first try, again, just step through the code and it'll make more sense as you do it. So let's pass it. So again, so we pass it through QKV. And we want to do, okay, fine, x.shape, right? It's exactly what you think it is. And then QKV.shape, you can see it's been upscaled. So we now have 768 to 3 times 768. So this number here. Now, what we want to do is, we know that, how did we do it before, right? So we have a, let me check here. So our 768 was split into number of heads times the embed dim, right? So it was, in our case, right, if we have 12 heads, which we define here, num heads is 12, we want the 768 to become 768 times, or 64 times 12, right? 64 times 12. So so this one right here, this head size will be 64 for us. The num heads is 12, and so those two should multiply to 768. So let's start with that. So we have QKV will be equal to QKV.reshape, right? And it's going to be batch, like before, because we have 2, right? Then we're going to have patches, right? So we're going to keep the 197. And then we're going to do self.num heads, and then self.head size. Now this would give you a 2 by 197 by 12 by 64. 12 times 64 is 768, not 3 times 768 like QKV is, right? Because QKV is 3 outputs 3 times 768. Because we actually need to repeat this calculation we just did 3 times, right? So it's happened 3 times already, so we need to stick a 3 in there as well. And this will give us a, if we look it up, or print QKV.shape, you can see we have a 2 batch size by patches. For each Q, K, and V, right, query key and value, we have 12 unique heads, each represented by a dimension of 64. So that's where this tensor comes from. Now, we need to be able to grab Q, K, and V individually, right? But we can't do that right now because our index 3 is in the middle. So we're going to do a permutation to bring 3 out to the front. So we're going to do QKV is going to be equal to QKV.permute. And so we need 0, 1, 2, right? So the 3 dimensions in the second, or our 3 is in the second dimension right now. Then after that, we want the batch size, which is at 0. We want the number of heads now, so that's going to be our numHeads, or self.numHeads. So it'll be self.numHeads. Actually, no, we don't need to do that. our self.numHeads is 12, so that's 0, 1, 2, 3, so it'll be 2, 0, 3. Then we need our, for each head, right, we're going to have the number of patches, right? So that's going to be 197 right here. So that's in our index 1. And then we have 4, which is our last dimension that's left. 0, 1, 2, 3, 4, right? So 64. Let's quickly look at what this looks like. So this says we have a query key value, that's the 3, each of them for 2 batches. Each sample in a batch has been represented by 12 heads, and each head is representing 197 patches, and then each patch has 64, is embedded in 64, right? So that's where this comes from. This is probably the most confusing permutation and probably the most complicated thing we're going to be looking at today. So doesn't make sense, it's okay. Just step through the code, it'll make more sense the more you do it. So Q, K, and V will be equal to our QKV 0, and then we can just repeat this 1, 2. So it'll be 0, 1, 2. And so now we can print Q.shape. And notice how we're back to exactly what Q was before, right? Q was a batch size by the number of heads by 197 by 64, right? This is exactly how it was before, so that's how we're going to do it now. And so when we do the matrix multiplication, right, we're going to have a 197 by 197 for all 12 heads. The only new dimension is this 12, right? Because we have to do this computation across 12 heads rather than on just, a single head. That 12 wasn't there before. So, okay, cool. So now everything else is identical to before. So I think I can just grab most of it. Let's see. I can just copy it from, well, here, let me just copy it from my reference code just so I don't have to debug too much if something always manages to go wrong, right? So this is all the same as before. Now that you have QKV, our scaled attention matrix, where it'll be Q times K transpose. Our attention, we're going to do the softmax. I drop out a weighted average, right? Our attention times V. Then we need to do, and then we have a, here, let's return out here real quick. Once we have this, we now need to actually transpose it. So our weighted average is going to be batch by the number of heads, by patches by head size. We're going to transpose 1 and 2. So it's going to be, num heads and patches. So instead of having, because remember, right, our num heads, so X out of there. Our number of heads is 12, and our patches right here, our patches, where am I at? Here we go, sorry. All right, so the number of heads is 12, and the head size is 64, and we want it to be batch by patches plus 1, 197, by 768, which is going to be num heads times the head size, right? So we need to transpose these two, so we get batch patches num heads head size. So basically we flip these two, and then we just flatten along the last two, and it gives us back our batch, patches, and embed dim, which then goes through a projection to kind of, again, get to know each other, and then we return the out. I know this is a little, this is kind of complicated. It took me a couple passes to understand it, but this is essentially how we can do the entire multi-headed attention in parallel with a single QKV linear layer, and then a single projection linear layer. Cool. So that covers that. That covers kind of all the attention stuff. Now is the easy part, for the most part. There's a little bit more finicky stuff here and there, but for the most part, it's pretty easy now. So we have, this is a typical kind of, or at least a part of that picture you always see in the attention is all you need paper. You can see after we do a multi-head attention, you have something called add and norm, which we'll see in a bit. And you also have this feed forward, right? And this feed forward is what we're going to call our MLP, or multi-layer perceptron. And it doesn't really give you much details of what it's exactly doing here. But if you look at the implementations on like Hugging Face and stuff like that, you'll see exactly what's going on. So we're going to go ahead and just put it together. So this is just a set of very simple linear layers. We're going to have class, MLP, right? And then dot module, just like always, def init, self. We're gonna have input features, right? So how many input features do we have? We're gonna have a hidden features, right? Some hidden layer in the middle, and then out features. Now, our in features and out features should be identical, because again, each transformer should return the same shape always. So whatever the in features are, it has to be the same as out features. But just for clarity, I'm just making them two separate things, even though they have the exact same value. P equals 0. Super dot init. Okay, cool. So what we need to do now is just define a couple of things. So we're going to do self.fc1 is equal to nn.linear. Again, in features, hidden features, right? Where the hidden features in the middle. Then we have self.activation. The transformer architecture seems to like using the the Gaussian linear unit activation, so we're going to just stick to that and just use that. Self.fc2, right, is going to be a second linear layer, and then .linear, which is going to go from hidden features to technically in features, right? But again, for just clarity, we're going to do out features, even though in features and out features are the same thing. And then self.drop, right? We just need a dropout in there, and that's going to be equal to nn.dropout, and with a MLPP, right? That's our proportion of our dropout. That defines everything. Now just a quick forward function self x, and this is going to have x equals self dot the activation function around self dot fc1 around x, right? So we're going to pass an x to our first fully connected layer, do a activation function, then we're going to do x equals self dot drop x, right? So a dropout layer, x equals self dot fc2x, and then again x equals self dot drop x. Okay, cool. So this covers all of our simple forward function, right? So in features, hidden features. How we determine this hidden features will be something called the MLP ratio, which we'll see very soon. The idea is very simple, but basically, if our in feature is 768, they decided that the hidden features should be 4 times 768. But that 4 is called the MLP ratio. So if they're an MLP ratio of 6, then it'd be in features times 6, and then in features times 6 back to out features, which again is equal to in features. Okay, so that covers all of that. Let me double check. Yeah, that is all of that. So cool. Now, before we put together a single transformer block, we need to just quickly review again this, right? So we talked about this already, our batch norm versus layer norm, right? So batch norm takes samples, or basically calculates mean and standard deviations across the batch, where layer norm's really just doing it across the embedding for each sample individually. This is preferable for our case, mainly because if you have different sequence lengths, the batch norm doesn't make sense if you have a bunch of padding tokens on your sequence. Also, batch norm only works if you have enough samples to take that mean and standard deviation over. These models are pretty big, so you can't do that. It's also a pain to keep track of when you do parallel computing across multiple GPUs. So either way, the layer norm is the kind of default way of doing it. And because we're doing layer norm against the embed dim, we need to let it know what the size of that embedding dimension is, plus some EPS just for no divide by 0 errors. So let's put it together. So we have a class transformer block. So this is basically going to take everything we've done up till now and stick it together in a single module. So init self, and we need in here the embed dim again, which will be equal to 768. We need the num heads, which is going to be 12 for us. The MLP ratio will be equal to 4 for is the one they decided, but you can test different ones. MLPP is going to equal to 0. Our attention P is going to equal to 0. These are fine. You can play with different dropout percentages, and then efficiency efficient equals true, right? So do you want to use the efficient one or the other, the combination of the other two, basically? But so we need to do a super, like always. Let's go up one, super dot init, right? And now we need to define the norm. So we're gonna have a couple of normalizations here, because again, if you look at the picture, you have a add-in norm here, and then another add-in norm here. And we'll talk about the add part in just a bit as well. Actually, yeah, that's here too. So I'll talk about it once I get there. So let's just keep going. So we have self.norm1. This is going to be nn.layer norm with a input of embed dim, right? Because that's the dimension we want to do it against. So that's the length of the dimension we want to do it against. EPS equals 1e minus 6 e. There, cool. So that's self.norm1. This will actually be also our self.norm2 layer later on, so we can just define that right here for now. Okay, cool. So if we're doing if efficient, right, then we want self.attention is equal to efficient. I'm sure I spelled something wrong here, but it'll complain when we go to run it. Attention embed dim equals embed dim. The num heads equals num heads. Attention P equals attention P, and then the last one was the projection, right? So projection P equals projection P. Cool. So that's if we want to use the efficient one. I don't need that. Else, right, use the regular one. So this will be the exact same thing, except instead of efficient attention, it'll be called multi-headed attention. There we go. Embed dim equals embed dim. There we go. Cool. Just line these up again. Wonder if I spelled something wrong, but let's check. So we have efficient attention, multi-headed attention. All right. Well, we'll see if something goes wrong. Whatever. All right. So there's our potential attention. You know, which attention mechanism do we want to use? We have our norm2 right here. So that's our second normalization. You normalize once before you pass it in, once before you pass it into attention, once after you do it in attention, and after you do that, we need our hidden features, right? Features, right, for our MLP is going to essentially be just the integer of the embed dim, right, 768 times the MLP ratio is what we want. And so we're going to do self.mlp is equal to MLP, that thing we did before, in features equals embed dim, hidden features equals hidden features, and then embed dim equal, or no, not embed dim, out features equals embed dim, right? So we make sure we put it back essentially the way we found it, at the same shape, and then we have the MLP P equals MLP P to control the dropout. Good. So this is kind of a singular transformer block. The forward is pretty easy now. So forward self x. Okay, so this is where, well, let's just do it the way most people think about doing it, and then we'll talk about how to fix it. So we're going to do x is equal to the self.attention, right? And we're going to apply attention to the normalized x. So it's going to be self.norm1 x. Cool. And then x is equal to self.mlp, and it's going to be self.norm2 x, right? So we're going to first normalize x, pass it through our attention module, renormalize it again, and then do our multi-layer perceptron, and then we return x. Now, this is the way most people would think about doing a transformer, but there is a little bit of a problem, right? So, and this is the problem accounted in ResNet, right? Where you can't have a super deep neural network, mainly because backpropagation won't be able to make it back to the start of it. So, you know, how are they making these you know, like these transformer things, like I don't even know, like 96 layers deep for some stuff like the big GPTs and all that. Well, really, we have to somehow include residual connections here. So you should, you know, already know what a ResNet is and kind of the idea behind it. But instead of doing x equals something, we're going to do x equals x plus something. And by doing this, essentially doing backpropagation, we will update all the weights in here, but we can also essentially pass the gradients through x directly, so it has a new path to kind of flow back to the previous transformer block before any of this happens. So it lets it kind of skip all these annoying mechanisms and lets the gradient kind of keep working its way backwards during backpropagation. So there we go. We should probably test this and make sure it works. It's fine. We'll find out soon enough if it works or not. So, okay, so now we have to finally put it all together, right? We're at the end, right? So this is where we're going to instantiate our class token, our positional embeddings, concatenate and add them on. But really the big picture is we have this input x, that's patch plus 1 by 768, gets passed to a single transformer block. Each transformer block will have 12 heads in our case, so each one will output a patch plus 1 by 64 12 times. We concatenate them together to create this thing again. We use a linear layer to kind of aggregate that multi-headed attention, and then this output is the exact same shape and gets passed to the next transformer block, and rinse and repeat. And so if we have 12 blocks and 12 heads per block, we actually have 144 attention maps right inside it. So, and then to actually classify things, we just need to strip off that class token. Here I wrote it on the bottom. On the implementation, it's actually going to be on the top, but the idea is the same thing. We're just going to grab the class token, pull it out, and then just you know, use that to predict what we want to predict. So cool. Let's quickly put this together. This is kind of the easy part. So class vision transformer, right? So again, right, the hard part really was just implementing that the attention module, mostly the efficient attention. I think the other stuff kind of makes sense if you kind of look at the shapes and kind of think through what it's doing a bit. So I'm gonna actually just copy this in. This is a ton to type, so let's copy all of this in. Cool. Right, so again, image size, patch size, in channels, number of classes that we're trying to predict, right? For in our case, cats and dogs is 2, embedding dimension, the depth, the number of heads, MLP ratio, attention, MLPP, projection P, you know, all the good stuff. So that's basically everything we've done so far. So first we're going to do, right, the first thing we have to do is take an image X and do the patch embed, the patch embedding equal patch embed, and it'll be image size equals image size, patch size equals patch size, then we have the in-chans equals in-chans, and we have the what do you call it, embeddim equals embeddim, right? So those are all the things we need for a patch embedding: the image size, the patch size, the number of input channels, and the embedding dim that we're interested in. Cool. Next, we need to now define our self.cls token and self.position, or let's just call it pos embed. Right. So our CLS token, we're going to call them nn.parameter. So an nn.parameter essentially saves a kind of a set of parameters that are learnable. They're similar to a tensor, but it stores it as an actual module in your model itself, rather than just being some like extraneous tensor that exists. So this way you can actually count it as a parameter in like the number of parameters that your model like is trying to train. So parameter, we're going to initialize this as torch.zeros for now. It doesn't really matter. You could also probably normal or start them as just like a bunch of random random weights or random numbers, but either way, we're just going to do it this way for now. It shouldn't make too much of a difference. Cool. And the reason for these, right, so we're going to initialize these as 0, and we know we have dimension. Essentially we have let me think. Right, so we have currently the embedding dim. This will be 768, right? So our or 196, right? So we're gonna go from a, let's just write it out. So we're gonna have a batch size of 2 by the 197 or 196 right, by 768 is what we currently have. And we're going to convert this to a 2 by 197 by 768, right? So we're going to be concatenating something of size 1 by embeddim to the bottom here. Now the thing is that this class token has to be repeated, the same set of class, that same class token has to be repeated for every batch, right? So that's what this is kind of sitting as a placeholder for now, because we don't know what the batch size is yet. We're going to expand this to the number of batch sizes, so it'll end up as 2 by 1 by embeddim. So when we concatenate, it'll be 2 by 197 by 768. But for now, because we don't know, we're just going to set that as 1 and just leave it alone, right? So we'll expand that in just a bit. So second one, the positional embedding is easier to understand because we just need to add essentially a weight matrix of values, learnable parameters, to our thing. Again, we're going to start these as zeros, but you could probably, I think in the TIM implementation actually might use random, either way, I can't remember right now. So we're going to set this as, it's going to be again torch.zeros, and this is going to have a 1 by 1 plus, right? And it'll be 196. So we can grab 1 by 96 because in our self.patchEmbed, we had a attribute called nPatches, right, that we used to calculate the number of patches. So it'll be 1 by 1 plus self patches, or basically the number of n. So 1 by 7, or 197, and then again, just like before, embeddim. So this is going to be, so our class token is a 1 by embeddim. All we care about is the 1 by embeddim, and we're going to just expand this dimension out to the batch size so we can concatenate it onto the bottom. This one isn't concatenated, it's directly added. So the same set of values is just added across the entire block of samples you have across the batch, essentially kind of injecting positional information into it. So that's why we can just leave this as is, and it'll be 197 by 768. So there you go. There's our class token and the positional embedding. The only really new things we have, the only thing we need to actually do on top of that is a dropout, just to make sure they included it. So we're going to do position dropout. It's going to be nn.dropout, pause drop, drop. There we go. Cool. Now we need to do self.blocks. That's going to be equal to nn, right? So this is where we talked about we need multiple of these PyTorch, or these transformer blocks, nn.module list, just like before, right? And this module list is going to have a list in it. So let's create it this way. There we go. And this is going to have the transformer block. It's going to have embed dim equals embed dim. It's going to have num heads equals num heads for a single, number of heads in a single block. MLP ratio equals MLP ratio. We have the MLP dropout, so MLP P equal, or PP equals MLP P. We then have the attention dropout, so attention P equals attention P. We then have our projection dropout, so let's scroll down a bit, proj P equals the proj P, and then lastly, not an M, and then lastly we have efficient equals efficient, right? Do we want to use the efficient transformer or the non-efficient one? So there we go. So there's our self.blocks, and we just created a list of these, and it's going to be this for blank in range, and I think I saved it up here, image size, embeddim, num heads, depth, right? So this will be our depth. So I forgot to mention that, right? So the depth is the number of transformer blocks we want, and the num heads is how many heads we want in each of those blocks. Yeah, sorry about that. So yeah, in depth is what we want. And then again, we need to normalize. So self.norm equals nn.layer norm. For the same reason, it'll be embed dim. EPS equals 1e minus 6. Again, nothing has changed there. And then self.head is going to take nn.linear. It's linear. It's going to take a shape, or it's going to take an embed dim from the class token specifically, and we'll see that in a bit, and output n classes. And there we go. That initializes everything we need. So now we need to do the forward function. Forward self x. And now what we're going to do is we're going to first figure out what our batch size is, right? Typically this would always stay the same, but at the very end you might have a slightly smaller batch size, just depending on how you're grabbing your batches. So we're just going to grab the batch size every time. X equals self dot patch embed x. Actually, this would be a great place for us to pass tensors so we can see how things are changing step by step. So let's do this. So vision transformer, leave all the defaults, rand. So we're going to start with a random image now. So it'll be torch.rand. It'll be 2 by 3 by 224, 224. Again, if we check, rand is this thing. Good. So what we want to do is VIT and pass in rand. So now we're going to do x dot, we have to print x dot shape, right? So we can see after we do our patch embedding, our image of size 3 by 224, 224 is number of patches, actual patches, 196 by 768, which is great. Now we need to actually concatenate to the bottom of this our class token, right? So we're going to do CLS token. We're going to create a new one here, CLS token. So this is not self.cls token, so we're not going to replace the thing on top. It's going to be torch.cat, or actually, no, I need to do self.cls token.expand, right? And we want to expand what? To batch size, right? So we want to make sure we have the same batch size, and then the other two dimensions can just stay the same. So we're going to print CLS token.shape. And you can see CLS token is a 2. It was a 1 by 1 by 768. Now it's a 2 by 1 by 768. And we want to concatenate on this dimension, right, where the 1 is. So our 196 and the 1 will make 197. So this is the part where we're going to do our x equals torch.cat, right? We want to concatenate together what? So we're going to be putting the CLS token on top, but it doesn't really matter where it goes because our positional embedding will, it'll encode where the CLS token is in relation to everything else. So whether we put it on the top or the bottom doesn't really make a difference as long as it stays the same when you're training, validating, testing, and all that. So, and then we're going to need dim equals 1 because we want to do it on the 0 and then 1, right? The first dimension. So, okay. Then x equals x plus, or actually no, before I do that, let me print out x.shape just so, right, so we have 2 by 197 by 768 now, right, so you can see it's changed. Now we're going to do x equals x plus self.pos embed, right, so we're going to inject in that positional embedding, again, prints x.shape. This shouldn't change the shape in any way because we just added the same size tensor across our batch dimension, right, so we have a 197 by 768 positional embedding, and we just broadcast it across our entire tensor. So there we go. So there's our, there we go. We also need to just make sure we do a x equals self.pos drop, so our dropout, or not dropout, our positional embeddings don't, overfit. So we're going to do a pos drop. Cool. Now we need to do for let's print it out. Print self dot blocks. Right. We created these blocks. You can see each transformer block has all this fun stuff going on inside it, which is great. If we do you can see how it's all like nice and contained because you have a linear with in 768 out 2304. If we do efficient equals false, then you will see essentially it broken down where we have transformer block. Inside it you have multi-headed attention with heads, and it has 12 of those heads, and it just does this over and over again. Again, this is like a redundant way of doing everything in a single kind of forward rather than like iteratively building it. So we're going to do efficient equals true for now. Cool. All right, so we're going to do, so now we're going to essentially iterate through a block. So for block in self.blocks, right, so for block in self.blocks, we will do x equals block x. We're going to pass an x, and let's print out x.shape. Actually, let's print it out. Well, we already know it. Let's just add it here. So the first one will be here. Let's just put start, and then block in, for now, let's just add this in. It doesn't really matter for what we want, but just for learning purposes, idx, print all right, what went wrong? Forward function block in self.blocks, a transformer block, oh, whoops, this forward is inside the other, oh, I did that again. This forward is inside the, right, so it was just the wrong, there we go. Yeah, now it should work. It was just inside the init, which doesn't work, so, okay, good. So now this should just work. Nope. What else is wrong? Unsupported tensor of tensor and none type. All right, so let's see what that is. Well, let's just test it here so I don't have to keep scrolling. Okay, so transformer block, let's call it TB equals transformer block. We're going to leave all the defaults in there. All right, so we got to debug this together now. This is always fun. All right, so what we need to do is create a rand is torch.randn. This is going to be 2 by 196 by, or 197, I guess, by 768. And let's print out rand real quick. There we go. And so let's do tb rand and see what goes wrong. All right, so we have x equals self.attention, so something has gone wrong. I bet it is that I forgot in attention to, here we go. So this needs to return x first of all. So that's not going to work. And I think for attention, we're returning out. Okay, good. So I was just not returning the output of MLP. There we go. All right, cool, easy fix. And you messed up something. It's always something. All right. Cool. So let's try this one more time. There we go. Okay, so we have the start is of size 2 by 197, 768, and notice how for the output of every block is the same as the input to every block, right? And this just lets us stack as many transformer blocks as we want. We can make the embed dim as big as we want. We can make the number of heads as large as we want. And really, the only like novel, I mean, obviously there's more that goes into this, but the reason things like GPT and BERT work so well is really just the scale of the models rather than fundamentally what's going on, because technically it's very similar. The implementation is actually very similar to what we just did. There's just a couple nuances specifically to deal with, you know, text rather than images, but that's fine. So x is that. Let's get rid of this. X will update on its own. All right, so now that we've done all of this, we're going to do x equals self.norm, just normalize x one more time. And now we're going to print x.shape again. And what we'll notice, as we saw before, this takes a second because it has to, I deleted it. Whoops. Let's just fix that real quick. VIT is that. Rand is torch.rand. And it'll be 2 by 3 by 224, and then VIT rand. Cool. Okay, so our output, our final after normalization is 2 by 197 by 768. We want for every batch only the last, or I guess the first token because it's appended to the top with the embedding of 768. So our CLS token final, right, the final version of the CLS token will be x it'll be, I want all the batches. I want the 0 at the start, right? It's the first token on the top, or the 0th token, and then all the embedding dimensions. So print CLS token final. Rather than printing it, I'd rather see the shape, and it should be 2 by 768 because the middle dimension kind of just disappears because it's just 1. So essentially for every sample, we now have a 768 length vector representing it. Now in BERT, they actually added like an extra linear layer in between this and what we're about to do, but I'm going to try to, if you look in Hugging Face, it's called the BERT pooling layer or BERT pool or something like that. But I'm just going to try to keep this as close again to the implementation as possible. So we're going to do self dot, or x equals self dot head CLS token final, which will take our 768 embed dim and map it to the 2 classes of interest, right? And that kind of covers our vision transformer, which is exciting. We're going to output x, right? We're going to return our x. And just for visualization later, you don't have to do this, but if you train a model and then you can essentially this way grab your CLS tokens for all your samples and then do like a t-SNE plot to see how your dogs and cats are like clustering, for example. But that's fine. That's just in there. So if you want to try that out later, you can see how it works. All right, so that should do it. So now we can go ahead and do a quick training script. Now I'm going to assume everyone has trained a model before, so I'm just going to copy this in so I can avoid typing the whole thing. Right. So what we have here is we're going to pass in the model, the device we want to train on, number of epochs, the optimizer scheduler, a scheduler, right, a loss function, the train loader, right, and basically our training data loader, validation data loader, and like what we want to save it as. We're not going to actually train this model because it takes forever, but this is just to make sure it works. And this is your typical, right? For every epoch, we're going to kind of save these training losses and accuracies. We're going to iterate through a model. Notice that we're not actually using the class token. Right? We don't need it for anything because our model again outputs x and the class token. We just need x or output, calculate the loss, calculate the accuracy, update the model for validation, right? It's with no grad. Actually, there should be a model.train and then a model.eval in here. Right, so just we're training and evaluation. Right, we keep track of everything, save it, you know, pretty standard stuff. So what we're gonna do now is just make sure that the model works as intended somewhat. So we're gonna define our model here. Notice that I picked a smaller embed dim, smaller depth, less number of heads. Again, this model's surprisingly, it's a big model, right? If we use even the VIT base, it requires a little bit more, GPU horsepower to kind of do that. But we can actually take a quick look here, right? So we have this here. I'm not gonna type all this, but essentially what we're doing is we're iterating through all the parameters in our vision transformer. And for each one of them, we're grabbing the shape of the tensor that represents the parameters for that specific block, and then just multiplying together to get the number of parameters that we have. So if we print this out, we can see this has a, let's see, 1, 2, 3, 1, 2, 3. So this has a 11 million parameter model, right? If we do 768 by 12 by 12, we have a 85.8 million parameter model, right? So it very quickly becomes bigger. The other thing you can change is this, the patch size, right? So the patch size in our case are 16 by 16. You can actually, there's also a VIT8, right? So basically your patches will be smaller, indicating that you have more patches, right? And so, right, you can change all sorts of stuff. So it's really just up to you, right, what you want to do. But either way, let's just use this as our model. 85.8. Oh. Cool. Now I will just copy the rest and just talk through it, because you should have already done something like this before. Here we go. Let's grab this. There we go. All right, so what we're going to do is we're setting up the path to the data, which is incorrect because the path to the data is this one. So I saved it up here. Great. So here's the path to the data set. There we go. Right, so we're going to use typical image folder. I set up the data set in that way. We're going to normalize with our ImageNet, kind of normalizations, mean standard deviation, training, transforms, validation. Really nothing fancy is happening here. It's super simple. We're going to split our data set into train and test. We're going to apply those transformations into the pipeline. We're going to train on CUDA 1. We're going to train for 100 epochs or whatever. The thing that I've noticed that works best is using the schedulers. So I've seen that these vision transformer seems to react pretty well to like cyclical learning rates. So you can play with different ones and see how it goes. Loss function is very simple, right? We want to do a cross entropy loss, batch size of 128, and right where we can basically just train. Let's see what went wrong. Train is not defined. Oh, I didn't run the thing up here, did I? There we go. And what is it this time? Let's see. K transpose. Oh, I am running out of memory. Why is that? Oh, because I'm trying to train the full model. Right, that's not going to work. So yeah, I'll later do a kind of an addendum to this where we're going to essentially try to train this model, the base model, but we're going to use multiple GPUs to do it right. So that'll be a distributed training thing that I'll kind of add on later. But for now, let's see if this trains. No, not yet. I think I might have to restart and run the kernel. So let's do that. Kernel, restart, and run all cells. Actually, just to make sure it works, let's just drop the batch size down to like 32 for now. Kernel, restart, and run all cells. Cool. Yeah, again, this model is, these transformer models are very, very large. So they are, tough to train. There we go. Now it's kind of ripping away. Right, so while that's happening, we can quickly check watch n 0.01 and vid SMI. Right, and we can see, right, it's using, looks like it's using like 10 gigabytes of memory to train this, which is good, right? Not so bad. All right, yeah, perfect. So that basically concludes the vision transformer tutorial. Now, I do want to mention all this stuff, all the non-vision related things. So that patch embedding was unique to the vision transformer. Actually, honestly, the patch embedding was the only unique thing to the vision transformer, because this whole transformer block we wrote with multi-headed attention, you can directly use this with GPT to train like a GPT type model or a BERT type model. There's only one main thing that needs to be changed before you want to train GPT, which is basically forward prediction model, is when we calculate our attention matrix, we basically want to set the attention to 0 to future samples. For example, if we have the sentence like, my name is Priyam, when we have the word my, we want to predict the word is, right? So we wouldn't give it the answer. So you'd have to zero out is name, my name, or sorry. All right, let me just type it out. So if we have my name is Priyam, right? If we have the word my, we want to predict name. So you don't want it to actually see name is Priyam. Otherwise, it'll just, you're basically giving the model the answer, right? It's trying to do forward future prediction. So that doesn't really work out. When we do my name, right? So that when we have the word name, name can look back on my, because my already exists, but it can't see is Priyam. When we have my name is can look back on name and my, but it can't look forward to Priyam. So on and so forth, right? So the only thing you have to really do is do a, basically zero out the top triangle matrix of your attention. Maybe we'll do that in a future video for our kind of GPT, more basically this in an NLP case study rather than our kind of vision transformer. But for now, you can already see it's already at 60% accuracy, and this just takes a while to train. So also I didn't really set the either way, right? You have to mess with the different, these tend to overfit pretty quickly. So either way, this is kind of the full-fledged implementation of the vision transformer. Hopefully this is helpful. Again, the implementation will be on GitHub. It'll be shared with you. Please take a look at it, especially the efficient attention. Just take a look. Make sure you understand the shapes, because there's a lot of kind of little pieces going on. Now's, I guess, a good time for you guys to ask any questions, and then I'll show you some other cool things about this that you can do.
Yeah, I had one question.
Yeah, please.
So I'm just trying to make sure I understand this right. This particular vision transformer, we don't need the encoder because we're doing our own custom embedding, correct?
Correct, right? So are you talking about the this piece here?
Yeah, in the Vasawani transformer, yeah. So
Yeah.
we're just doing our own like linear projection to do that encoder layer, right?
Yeah, so I'll kind of explain what's going on here. So essentially, in language translation, right, you're going to have a Spanish input and then like a English output, right?
Yeah.
And let's say the Spanish input's like me llamo Priyam, right? Which the English is my name is Priyam, right?
Mhm.
Well, you encode the entire input, right? So the input is known to you, right? You know exactly what the input is, so you can actually look forward, you can look backwards, you can do full multi-headed attention on the input, right? And now with me llamo Priyam, with the attention, with basically the transformer representation numerically of me llamo Priyam, it's going to pass something to the multi-header attention, and it's going to, the output embedding will just be a start token, right? It actually won't be anything. It'll just be a start token. And the goal is, given the start token and not being able to look forward to my name is Priyam end token, right? It's going to need to predict my based on this information.
Yeah.
Then the output here will be my. This output then goes back and gets concatenated here. So now you have start token my, and this attention flows in again. And now you're gonna have to predict my, for my you need to predict name, and then name is predicted and goes back down. But you can see why you would need two blocks, right? Because you need to encode kind of two different things at the same time, where in our case, we're just encoding an image, right? Specifically an image. So we only need a single regular multi-headed attention. There's no masking needed because we can look at the entire, I mean, the whole purpose is to look at the entire image at once, right? Some examples of where you might see similar, though I don't think it's exactly the same, but similar structures, I guess, is like the, if you've ever seen like Clip, which I think OpenAI put out a while back, but Clip is basically to, in an unsupervised way, learn relationships between text and images, right? So if you want to learn stuff between text and images, you need a text encoder and an image encoder, right? So it's kind of the same idea. Does that make sense?
Yeah. And then the second part of the question that I didn't get to was, so my understanding for conventional transformers is that the encoder is somehow responsible for defining the keys and the values, and then the decoder uses the queries. So like for like self-attention, is that all those three come from the same place, whereas for this conventional transformer, the encoder is defining the keys and the values? Is that correct?
Yeah, no, you're right on. You're on the right path.
Okay.
Yeah. So in our method, we want to use all queries, keys, and values from the same place, right? Because they're all coming. Well, they're all generated from the same data, but you need a way to share information, right, between layers, between like encoders, right? Your input encoder and your output encoder. And so the easiest way to do that is like, oh, let's just send my queries and keys over here and use the values from here, and then just kind of do the same calculation. Yeah, so you're right. Because we do have some extra time, I do want to show something that could be of interest. So this is something I did a bit ago. If it wants to load, there we go. So in this, we did this work last year of basically exploring unsupervised segmentation. Well, once it loads, I guess. I don't know if it's going to want to load. Oh, okay, slowly but surely it will load. Is there any other questions though while this is loading?
I did have a question. Sorry, please go ahead. Hello?
Okay, my question is about like splitting the QKV like from the big super matrix into like K and V matrix. So when we are kind of reshaping it, are they split it like line by line or just or does this QKV is just kind of big chunk of juxtaposed QKV matrix, or are we just slicing it?
I think it's the second one, right? So notice how we didn't reshape anything, right? If you reshape things, the values that go with each dimension get all jumbled up, right? So we never reshaped. We permuted it for a reason. And so when we right, because that dimension 3 was in the middle, right at the beginning, because we did 3 times, right? And we needed to move that to the beginning, move it from the middle to the beginning. And so when we did that, we needed to make sure that the basically we did a permutation. So the queries, keys, and values are still in that same order. It's a bit more finicky. So someone brought up a bit ago, like, oh, like, but it's the same weight matrix now. So isn't it the same calculation? And although it is true that it is the same weight matrix that's being used to generate all QKV in that one linear layer, we're using different parts of that weight matrix for each Q, one for K, one for B, if that makes sense. Yeah, so as this loads, right? So if you actually plot the attention maps, right? This is just one example. You can see, this is like an easier example, but you can see how the attention maps almost look like segmentations, right? This one seems to focus on the ship. What's cool is that if you look at different attention maps, so this was a VIT 12 by 12, right? So 12 layers, each with 12 heads. So you have 144 attention maps that we could potentially plot. And you can see some focused here, some focused on the bridge, which is the cool thing about these vision transformers. You can actually, in terms of like explainability, transformers have kind of allowed us to do a ton of really cool stuff that we weren't able to do before. You can see how this one really focuses on the bird, but completely ignores the thing that it's standing on, right? Because this was trained in an unsupervised manner on ImageNet, where bird is like a pretty common class in ImageNet. So you can see in this one, this is just like examples of how attention can be used for segmentation. So when you actually, if you actually wanted to use the vision transformer, basically what we just did for segmentations, all you have to do is grab those attention matrices specifically and output those to maybe some other type. You could even use convolutions at that point to actually output these segmentation masks. But yeah, this is just an idea of ways you can do things. Someone else had a question, but I don't know if you answered this, but where can we get the dogs v cats data set? Oh, I think Kaggle should have it. I just downloaded it off the internet, so you should be able to find it. If you want to use Hugging Face, Hugging Face has it too. I use their dogs v cat thing all the time. I think if you have an account on HAL, I know I stored the data somewhere on HAL for people to access, though I don't know if it's just for the summer program or if anyone can access it. I could ask Dr. Kindertenko later to see if we can make, I don't know. I think they have a data set like repository available to everyone. But regardless, you can always just download it.
Hi, I have a question as well. A couple questions. First is, when you're doing the sequence of blocks there, the transformer blocks, and then in the very end, you only get the CLS token, it seems to me like there is a number of parameters on the very last block that are completely undetermined, right? Because they connect to the other tokens, to the other patches, and they get discarded. So there is no gradient that flows through those guys. I'm sure they don't affect the gradient flowing to where it needs to flow, right? Because you're taking it from the CLS token, so that's fine. But it just seems like it's a little bit of a wasted computation there, right?
Yeah, I do think so. I've never actually fully understood why they decided to do the CLS. I'm sure they tested a bunch of stuff, and this just somehow worked the best. I think intuitively it's a little bit off, but the reason the CLS token works, right, in terms of how are we aggregating information, right, into the CLS token? Well, the CLS token initially starts as like a bunch of zeros, right? Nothing really fancy, right? Just a list of zeros. But when we actually get to this step, right, where we calculate the attention matrix, one of these rows, how is the CLS token specifically related to all the other patches, right? So the weights between CLS and all the other patches. And then when we actually multiply by V, right, that's where we do that projection of like, oh, the CLS token is actually some linear combination of all the preceding patches. And I think that's how a lot of that information gets pulled down. And by forcing the model at the very end to only use the CLS tokens, I think it makes the model basically say, okay, if this is all I have, then I have to somehow move it down there. And because the CLS tokens are learnable parameters, right, the gradient update, I guess, would force it to kind of move in that direction. But that's that. I think that's the general idea.
No, that's completely understood. It's just a comment, I guess. It seems like in the very last block, there is a little bit of waste computation for outputting all of the other patches when you only need the final patch. But for everybody else, for all the n-1 patch blocks before, then it's fine. They are truly engaged into the final calculation, so that's not an issue. And the other question I have is sorry. The other question I have is, can you comment on placing limitations on the Q, K, and V matrices? For example, I know this is an image, so you want to match every patch against every other patch, and there is no causality. But if it was a time sequence, could it be the case that imposing a triangular structure, for example, would enforce causality?
You're exactly right. So actually, what we end up doing, right, is so we have our attention matrix here, right? You can still see this, right? I'm just making sure.
Yes.
You have your attention matrix. Now, you are correct, right? We want to make sure that, because this is sequence, right? So this could be, like, let's take the word apple, right? A-P-P-L-E, and then A-P-P-L-E, right? Apple and apple, right?
Right.
Of 5 by 5. So we want to make sure when we're looking at A, right, or the attention of A can only be related to A, the first A, because they cannot look at future stuff, right? That doesn't make sense for like GPT types of models we're generating. You are correct. When we're at the second letter P, well, P can be related to the previous A and the current P, but nothing afterwards, right?
Yep.
So what we actually do is we're going to set in a triangular fashion, right, just the way you mentioned it, all of these values to negative infinity, right? We set them to negative infinity specifically because when we actually go to do the softmax of negative infinity would just be 0, right?
Oh, I see. So right. you do it like, I mean, you enforce it to be like that, minus infinity, but it's within the calculations, right? Like there is no sort of lower triangular linear layer. You just like have a regular linear layer, but then just
we just zero
force
out
the parameters to be
zero.
Oh, okay, I see. Yeah, and in the same vein.
Yeah,
yes,
go
please.
ahead. Sorry.
No, I was
so
just
inherently. I just want to make sure that we're on the same page, right? So what ends up happening is, I don't have the updated one here, but basically when we do this times V, right? I showed you how it's really just a linear combination.
Yep.
Right. But when we're at letter A, we can only use the embedding for A. When we're at letter P, we can only use the embedding for A and P, like sequentially, right? So we can't actually, it doesn't allow for forward looking. So yeah, you just negative infinity and then softmax of negative infinity would obviously put those to 0. And that's kind of the trick that GPT uses.
Ah, sweet. I didn't know that. And in the same vein, I was thinking that, for example, if you place limitations on the Q and the K and V matrices to make it look like, for example, convolution matrix, right? Like what's it called? Venn diagonal or something, right? Like it's kind of funny because you go back to convolutions now, right? It's kind of a transformer model. But if you just look at the Q, K, and V matrices with limitations, you can go back to placing convolutions on it. It's just a curiosity. It's just something that crossed my mind. It could be interesting.
You technically can. Actually, you might want to read the paper about conformer. They basically use transformers and convolutions in the same model.
Cool.
It's for speech, that specific paper, but I'm sure the principles are still the same. So I would I don't remember right now kind of the details of that. It's been a while since I've looked at it, but you'll probably get an idea of an approach there potentially. And I'm sure there's I know for sure there's definitely like for vision tasks, there's like transformer plus convolution stuff, because like we've kind of shown in the very beginning, right? The convolutions focus on local features where the attention mechanism of the transformer lets you look at global features, but obviously having both would be the best of both worlds. So how do you mix both of them essentially?
Nice.
Yeah, so ton of stuff. I think one potential one, you can use some convolutions initially, and then basically on the outputs of the convolution, you can then convert them to tokens and do transformer kind of stuff. I'm sure there's a bunch of ways of doing it. So yeah.
Perfect. Thanks a lot. Thanks for a great presentation. Thank you very much.
No, I'm glad. I'm sorry it kind of like broke in the middle, but yeah. Does anyone else have any questions? Can you clarify in an attention match? Why would A patch to A patch dominate the output? Oh, it doesn't have to necessarily. Like intuitively, probably like you probably shouldn't. Like a patch shouldn't really matter to itself. It should focus more on the other ones. So I'm sure if you plotted the attention matrices, you'd probably see that self attention isn't super high typically. But it also could be, right? It just depends on how it turns out. I'm trying to think of an example in like NLP where maybe like there's specific words in a sentence that are really important in terms actually this is a pretty good example. Let's say you're doing like sentiment classification, right? You can probably use BERT or something like that for sentiment classification. And words like happy on their own are super important to predict whether something is happy or sad, right? In terms of like the sentiment of the sentence. So in that case, you would want to have attention to yourself. It's like, oh, I'm happy, and me myself is super important in predicting the sentiment of this thing, where other words may not be as important, right? And so it's things like that. That's probably like a very like stupid example. I don't know if that's even correct, but I guess that's the way I think about it.
So no, I guess my question was, in the calculations, if it's a projection, wouldn't if it's like Apple, wouldn't the A always project strongest to itself? Is there something else? I feel like I'm missing something in the way it's the linear.
That's what you mean. Like, why is it not just A just over and over and over again?
Or no, or it's more like if you have Apple as your query and your key, wouldn't the diagonal values always be highest if it's doing projection?
Not necessarily, right? Because we force the diagonal values to add up to 1, right? But there's our goal, right? In Apple, right? In the example of Apple, right? Our goal isn't to predict like the image classification like here. It's to predict the next token, right? What the next word should be. And obviously the current word, maybe Apple, but if we think about it in like a words for a sentence, maybe the current word obviously is very important to predict the next word, but there is like, there is importance to also previous words to predict the next word. And what if you're like a filler word, like duh, right? Duh doesn't add anything, but previous words, right, might be more important than the word duh. So that's where the self-attention of like duh to duh would be very small, where the previous ones would be higher. Does that make sense?
No, I guess my question is like, where is it that it becomes small? Is it because of the linear transformation?
What becomes small?
Well, like what makes the diagonal value small as opposed to when I look at the calculation?
I see. The diagonal values don't have to be small. These values can be anything, as long as it adds up to 1, right? There's no reason for the diagonal value to be small. Yeah. They could be, they couldn't be. It just depends on the context, right? Like if we're looking at the sentence like my name is Priyam, right? When we're looking at the word name would probably have a pretty high amount of salience with the word Priyam and some salience with my, because who does the name refer to? Probably not as much with is. right?
Okay.
And maybe name to name also has a pretty high amount of salience. It just depends. Now, is doesn't really add much, right? Maybe is to is doesn't mean anything, but I don't know. I'm not really sure. I'm mostly on the like vision side of things. I'm like kind of dipping into the NLP stuff. But yeah, that's kind of my intuition, I think, on how it's all working out. Yeah, I hope that kind of helps.
Well,
yeah,
just
there's no
let me ask the question.
restriction.
Let me ask the question a different way. Before the attention matrix, what are the learnable parameters in the sequence? It's the linear
Before
transfer, like
attention?
it's a linear transformation, I guess, that creates the embedding into 768.
Oh, like this, right? So yeah, it's just a linear, just basically indexing
Yes.
some kind of weight matrix. You can
Okay.
actually do pretty well on a character level. So if you go once the Git repository is short, but if you look up Min GPT, I believe it's called, it's by Karpathy, posted it a while back. He basically did a bigram model using only the embedding. So there's no learning. The only thing is you have this matrix of like 768 by the number of possible like characters you can have in a sentence. So like uppercase, lowercase, and exclamation mark, period, space, stuff like that. And you get pretty good like words form. It's just sentences don't really make a lot of sense, right? So at that point you have to go at the word level, or like you have to tokenize it somehow. You can do word level or like parts of words.
Okay.
Like maybe
Yeah,
a letter.
that's helpful.
Yeah. But that, yeah, please look at the so actually the way I've actually always done the attention stuff was that efficient attention that I went through later on of the entire thing happening at once. It was actually through his GPT implementation that I was going through, where I learned that, hey, you can actually just do it in like, you can do a single head and then concatenate the heads together, which I think is a little bit clear for people. It's clear for me when I'm like, oh my God, this makes so much more sense now. But yeah, that's the idea. Hey,
Okay.
I hope that's helpful.
Yeah, thanks.
I guess that's it then. Again, sorry for any technical issues that was there. But if you guys have any like specific questions, I think my email was on the invite, so please just email me, or whatever you need, and I'll try to help out. There's like a lot of cool stuff that you can do with this code. Like I was like generating like Harry Potter stuff a bit ago, and that's always fun. So yeah, thank you.